You switch on the light as soon as you enter a room. You never even stop to think about counting how long it takes for the bulb to light up. You couldn't. It's as if it's instant. Well, technically you could if you were fast enough. Good luck clicking that stopwatch in time when you're measuring over 670 million miles per hour. That's 180,000 miles per second. Almost the distance from the Earth to the Moon in the snap of a finger. Oops, wrong sound effect. Can you give me a finger snap? Yeah, that's it. In the snap of a finger. And the Moon's further away than you probably think. If all the planets in the entire solar system were lined up in one epic conga line, they'd fit between the Earth and its satellite. And that's including poor outcasted Pluto. Okay, light is fast. Moving on. It's a beautiful sunny day, perfect for a jog. And like any other day you go for a run, you stop and think, hey, I wonder what the speed of sound is. Don't you? Well, definitely not nearly as fast as light. Need proof? Check for yourself next time it storms in your area. You'll see lightning flash before hearing the crack of thunder. The light from that bolt rushed to you, zoomed into your eyeballs, and up into your brain for you to understand, oh, lightning. All the while, the sound wave from the thunder is still on its merry way to your ear. It'll get there, just give it time. By the way, thunder isn't the sound of storm clouds crashing together. It comes from that very same lightning bolt. It races toward the ground and rips a path through the air as it does. The air politely moves aside to make way for the lightning, and in the instant the lightning's gone, boom! The air comes back together and makes the sound we call thunder. Oh, and here's a fun fact. Sound travels faster underwater than in the air. A little over 4 times faster to be exact. So if you were to go for a swim with your friend and shout something bizarre underwater, they'd hear it a bit sooner than if you did the same thing outside of the pool. Uh-oh, everybody else heard it too. Oops. Sound also travels over longer distances underwater. It's why humpback whale calls can be heard for thousands and thousands of miles. But in a controlled environment where the air is dry and we have a constant temperature of 68 degrees Fahrenheit, the speed of sound is about 760 miles per hour. Now, that's a more realistic number, one that people can even reach. The famous Bell X-1 aircraft was the first to break the sound barrier on October 14, 1947. Test pilot Chuck Yeager was in the cockpit of the rocket plane. Imagine hearing that sonic boom for the first time ever in history. Bravo, Captain! Humans can race with sound, but light is a whole different challenge. For one, measuring it in the first place is no easy task. The official speed of light has changed several times throughout history, even going back to the 1600s. After centuries of debate and experiments with different results, the scientific community finally settled the matter in 1983. Maybe. To measure the speed of anything, you'll need to know 2 things: the distance between point A and B, and the time it takes for an object to travel between those points. With distance divided by time, you'll have yourself the speed of light. But with every experiment done to measure light speed, there's always been an extra cog in the wheel that everyone overlooked, or rather brushed aside. When doing an experiment using light beams and mirrors, we've always included the light beam's trip from A to B and back to A. With equal speed and equal distance, we have ourselves a controlled experiment and conclude an official speed number for the books. Case closed. Let's celebrate! Not so fast. A certain someone in 1905 had something to say about this, and that someone put a theory out there that light can travel different speeds going forward and back. Still can't wrap your head around it? Well, let's take this example. You had a long day. You pulled an all-nighter at work and can't wait to sink into your comfy warm bed. You get on a bus and head home. The night's clear and there's zero traffic on the road. Before the wheels on the bus can even go round and round, you immediately conk out in the back seat. But right before that, you checked the clock and saw it's exactly 10 p.m. What? After a big bump on the road jolts you awake, you become aware of your surroundings. But you suddenly find yourself in the exact same spot as the moment before you fell asleep. That was a quick nap. But then you look at your watch and it's now 11 p.m. You fell asleep in the bus and missed your stop. You'll have to repeat the exact same route all over again. Bummer. What can you determine from this? Since the whole ordeal took you an hour, you can assume it took exactly 30 minutes from the bus stop to reach your house and another half hour from your house back to the bus stop. Sounds logical, right? In our physical bodies, such a conclusion makes perfect sense. But it was Albert Einstein who challenged this idea. With his reasoning, the trip could have taken 59 minutes to get home instead of 30 and 1 minute back to the bus stop. Or even vice versa. Since you were fast asleep, there's no way you can know. And this idea is what's keeping scientists and physicists up all night throughout the decades. When you get into light speed in space, then the mind-blowing stuff starts happening. It takes approximately 8 minutes for light to reach Earth from the Sun. So, light is super slow in space? Not really. Now we're talking unimaginable distances. It takes 8 minutes for our sun's light to travel over 90 million miles to our planet. That's something to think about when going to the beach. The sunlight that made your tan lines traveled so far across our solar system to reach your skin. Ah, how thoughtful. And you can get sunburnt even on a cloudy day. That's how powerful our star is. Now, imagine yourself living on Pluto. I know, its planet membership got revoked in '06, but hey, call me old school. Our former furthest planet from the sun is so far away, it takes 5.5 hours for sunlight to get there. No wonder it's always cold. The first planet in line is Mercury. The sun's rays reach it in a mere 3 minutes. Hey, that's probably enough time to listen to your favorite song. By the time the song ends, you, the Mercurian version of you, will be basking in the sun's glory. It'll be impossible to listen to that track in space since sound can't even travel out there. You know, no one can hear you scream. Oops, there she is again. Music is just vibrating air, and without any air in space, sound can't travel. That explains why it's so eerily quiet out there. Okay, can somebody take the scream girl down the hall? And while we're up in space, let's pay our neighbor a little friendly visit. Alpha Centauri is the closest star system to our own. And what fun, the trip is just 4 light-years away. That's 25 trillion miles and 137,000 years on the road. Yeah, don't forget to pack a big lunch. To put all that in perspective, it would take around 5,000 generations in a super shuttle traveling through empty vast space to complete the journey. And we won't be able to come close to the star. Oh, and that's just one way. Okay, I think I'd rather come back to Earth now. Whew, that's better. Now, the longing question, how can we measure the speed of light without that little dilemma about the return trip? Oh, I got it. Why don't we just measure the speed with a super high-tech camera and map it out frame by frame until we're able to write down its speed? Well, nothing's as easy as it seems in the world of physics. Because when filming the light through a lens, we're not seeing the light itself, but rather a reflection of it. We just circled back to square one. Okay, scratch that plan. Then how can we prove light is going the same speed to its destination as its reflection is back to point A? Does the one-way speed have a defined value that's not a constant? Well, this is the ultimate question among scientists, and so far, there's just no way of truly measuring it. Unlike the speed of sound, which is more conceivable, the speed of light might just be light years ahead of us. Yes, just more fun light facts brought to you by The Bright Side. See the tie-in? Okay, never mind.
The speed of light is the fastest thing in our universe. It travels across space, passing through Mercury and Venus to reach us, and it's slowing down. No need to panic though. The sun is getting weaker, but we won't see the effects of it for another billion years. In the vacuum of space, the speed of light is around 186,280 miles per second. Any slower than that, and humans would see the changes firsthand. There would be some awesome effects, like colors changing and the brightness of objects fading. We'd also notice some differences in everyday objects, their length and shape. Scientists created a simulation to see what would happen if the speed of light was slower. In a vacuum, the speed of light can't change, but if light passes through different materials and objects, it alters the way we perceive things. Light acts as a wave and a particle, meaning that it's a wavelength. The color and frequency are determined by the distance from crest to crest in the wave. It behaves similar to sound with the Doppler effect. Imagine you're standing in the middle of a busy highway and a honking car speeds through. Wow, that was loud. You can hear that whoosh-like sound of the horn because the moving object produces the sound while you're stationary. The frequency and pitch seem to change, but it's just the sound reaching your ear faster than it would if you and the car were both stationary. Light behaves similarly. The wavelengths change if the speed changes. Moving toward a light source and making the wavelength shorter will shift the color to a blue and violet hue. Moving away from the light source, and you'll get something more reddish. So if the speed of light slowed down to walking speed, we'd notice the colors changing when we approach an illuminated object. At the same time, the color would change around us and behind us. If you walk sideways, the colors you're walking toward would become bluer, and everything in the distance would become red. This information is useful to astronomers who are studying objects in space. If they're blue shifted, that means the object is moving towards us. And if it's red shifted, then it's going in the opposite direction. In fact, everything in the universe is red shifted, proving that the universe is expanding and getting further away from us. The slower it gets, the brighter it becomes. That's because the photons become more present for us to see. At this rate, we can see invisible light and increased intensity. You won't notice that effect much if you're standing still, but because of the Doppler effect, moving towards an object will have different colors and different light intensities. Another phenomenon we'd experience is time dilation. It's when you move at a similar speed as light and time decreases relative to someone who isn't. Space and time are relative. So if you're sitting at your desk wasting hours away, yeah, sounds familiar, doesn't it? All your movement will go through time and not through space. You're stationary, but you're still technically moving forward in time, slowly aging. The faster you move through space, the slower your movement through time will be. If you move at the same speed as light, then all your movement will be through space and not through time. To notice that, you'd need another person to watch you. You're not in a time machine. You're both on Earth, experiencing the same time flow. To you, experiencing this firsthand makes it feel like you're going faster, because you're getting a lot more movement in space in a given time. The closer you get to the speed of light, the smaller you become. Well, not really, but it depends on who's watching. If you're the one traveling at such a speed, an object nearby will seem small, just as someone who's watching you travel at the speed of light will think that you're smaller than you actually are. The simulation that the MIT scientists conducted showed that if the speed of light drops, everything will become stretched out like a pancake. If you see mountains in the distance and then run at the speed of light, they will appear further away. Objects will become distorted, and it will feel like you're getting to a certain place faster because time has slowed down for you. If you're standing completely still and someone standing on your left-hand side throws a cube-shaped object over to your right-hand side, then naturally, you'll see one side of it unless it flips around. But in this new reality, you'll get to see the front side wrapping around the visible side you're seeing. If you're moving at the same speed as light in an infinite space, everything will be stretched out as you reach infinite speeds. In a world where people can walk at the same speed as light, we'll perceive nothing as normal. We'll have to get used to the way we see objects. Every movement we make will result in drastic shifts of colors. Even turning your head to look at something will feel weird. Let's say you're in a supermarket buying groceries, and you walk from aisle to aisle. The milk at the end of the counter will look like it's really close to you. But when you approach it, you'll start to feel like it's getting further away from you. The milk will also look a bit red. As soon as you get closer to it, it will shift to blue. If someone is passing through with a shopping cart, you'll see it as a sort of 3D model of a shopping cart. The color will shift as it gets further away from you. It will appear far away, but it's right in front of you. In fact, we don't really know the actual speed of light. Physicists gave it roughly 186,280 miles per second, but that constant is just for them to calculate other scientific stuff so we can understand it better. The problem is that we can only measure light with light beams and mirrors, but it's not like all we have to do is point a light beam at a mirror and measure its original path and its reflected path. Einstein's theory of relativity states that the original path of light moving from the source to the mirror may not be the same speed as the reflected light from the mirror back to the source. Hypothetically, if it takes light 10 seconds to travel from the source to the mirror and then back to the source, then we can conclude that each trip takes 5 seconds. But Einstein's theory is that it could take 9 seconds for light to travel from the source to the mirror and only 1 second from the mirror back to the source, or vice versa, or maybe completely different numbers altogether. That's why it's so difficult to measure light. A breakthrough came out for scientists when they managed to slow down the speed of light to 0 without losing its brightness. They did this by using ultra-cold atom clouds made with photonic crystals. These crystals are materials punctured with billions of tiny holes where light can refract. But what if we lived in a world where light stopped halfway? You'd wake up one morning and feel like it's twilight. You'd open the curtains and see that many car lights are on, but aren't so bright. You turn on the lights in your room, but feel like the bulb is tapping out. You replace it with another one, but it doesn't do the trick. You turn on the lights everywhere in your house, but it's all just giving weak light. You're confused and try to check if there's a problem with the electricity in your house, but it seems to be working well. You check on your neighbors, and they also have the same problems. Even experts in the field can't understand what's going on. Hours pass, and it's all the same. All the light in the world seems to have frozen halfway. Your phone is low on brightness, even though you bumped it up to maximum. Everything is getting darker. You learn from the news that it's a global problem. Light is slowly diminishing, and soon there won't be any of it in the world. You decide to wait it out while everyone else is panicking.
Whoa, something doesn't feel right. Everything seems shaky. It's definitely not an earthquake, and it's actually getting worse. The clouds seem to move quicker than usual, and the animals are going into a frenzy. The news anchor pops up on the TV in an alarmed tone and says, "Good morning. We're sorry to interrupt your program. Scientists have just discovered that the Earth's rotation has been fluctuating at an unusual rate. A group of specialists believe that the Earth is increasing its rotation with every second, and they don't know why." Even if the Earth increased its speed by 1 mile per hour, the day would only get shorter by a minute and a half or so. We wouldn't really feel it, and you could go on like nothing is happening. But as the Earth spins faster, our bodies, which are adjusted to a 24-hour timing, will have a hard time trying to cope with it. If you live by the equator, that means the rotation of the Earth is going quicker than at the North and South Pole. The area by the equator needs more time in order to complete its full rotation from the starting point. You'll experience more rain than usual. The Earth's rotation keeps the weather consistent and balanced so that nothing abnormal happens. But because the Earth is moving so fast, the weather is acting up. We'll start to see more storms and more cozy days inside, sipping on hot cocoa. Even though it seems weird, everyone can go about their day. But if the Earth picked up some speed and moved at 150 feet per second, the day would be reduced to only 22 hours. It kind of makes you feel jet-lagged 24/7. Every business works with the 24 hours a day schedule, so taking away even 2 hours can have catastrophic effects on the world economy. The whole calendar will have to change and adjust to the new timing. Clock designs will change with the new midnight, replaced with 10 o'clock. And with each week, the hours will shorten, so there will be no proper way of telling time except by sunsets and sunrises. The weather will continue to get worse and worse, feeling like the rain will never stop. The animals that rely on weather patterns won't know how to function, and mass migrations will occur from almost all species of animals. Flocks of birds will be flying everywhere and reach places they normally won't go to, affecting the whole food chain and ecology. Woods, jungles, and other places where animals roam are kept in proper balance when unaffected by humans. If it constantly rains in certain areas, then floods will force animals to move to other territories and compete with the predators in the area. If the Earth picked up speed every day, then standing on a scale in the Arctic would tell you weigh 180 pounds, but around the equator you might weigh about 179 pounds. That's because of the extra force opposing gravity in that area. With the Earth spinning faster, all airlines around the world stop, since the radar systems have gone haywire and the weather is too dangerous to fly. Everyone has to get around by car. Satellites are positioned in such a way that it's crucial they remain where they are in order to bounce signals to us. Because of what's happening, Wi-Fi and TV signals can't go through. Communications around the world will end up short and slow, and eventually we'll have a total communication blackout. Ships will cease to operate, and global trading will collapse, adding extra damage to the already failing world economy. Winds will get stronger and faster than usual, which means temperatures will change. Storms like hurricanes will be stronger than ever and have more energy for destruction. And still, at 100 miles per hour, the equator will now be swallowed up in the water. The Amazon basin and small islands will now completely submerge in water by around 50 feet. Most of the plant life will be endangered, especially by the equator. With woods threatened by floods, more animal environments will be in jeopardy. The trees and plants won't survive so much flooding. If the Earth rotated so fast that the hours would now be reduced to 15, then we'd probably feel like we're always on a jet plane going through turbulence. It would be impossible to sleep if the Earth kept picking up speed every second of the day. So days would be around 7 hours long as well as nights. The whole world would be flooded, except for the highest points and the tallest mountains. If that happens, humans will most likely end up there clinging to the last remaining clear patches of land. Most of the animal life will be extinct as well. And as the Earth is spinning faster and faster, the crust will lose its durability, allowing more frequent and stronger earthquakes to happen. Volcanoes will erupt all over, even if they're submerged in water. It'll go on like this for quite a while. Many major natural disasters like earthquakes, tsunamis, volcanoes, and even melting ice sheets have sped up the speed of the Earth by milliseconds. So, with the Earth's continuing speed increasing, these natural disasters will make the planet go even faster. Even if it's just for milliseconds, it's enough to have major consequences. The Earth is now spinning at 1,000 miles per hour, and as you're sitting with the rest of the survivors, you feel yourself levitating slightly. You'll see tiny pebbles and rocks floating inches from the ground. The clouds above you are passing like shooting stars. The air is thick with moisture, since water is rising to the top, forming thick clouds ready to pour. But since gravity is weaker, some of the rain is suspended in the air. Many small objects will be floating around as if you were in space. The days and nights won't be longer than a few hours. At this point, the whole world will be flooded, and the crust will be 80% gone. If it goes on any longer, there won't be any living things around, probably except for microscopic creatures that can withstand extreme and harsh conditions. The Earth would need to spin at approximately 17,600 miles per hour to cancel out the gravity for things to start floating around. At this point, all the water in the ocean will rise and look like reverse rain. The large mountain rocks will separate from the bedrock and levitate above the ground, looking like little planets in space. The Earth is now spinning 17 times faster than usual, which makes one full rotation around its axis only 84 minutes instead of 24 hours. If you manage to stay that long, then you'll literally see the days and nights go by in an instant. You'll also be floating aimlessly in the sky, bumping into rocks and other surfaces. You won't recognize anything anymore. The Earth's crust is ripping apart, exposing the magma underneath. So landing on the ground isn't an option. You'll see outer space as you go higher and higher. You won't know how fast you're going, but all you know is that you're probably the only human left in this spinning world. The Earth will eventually spin so fast that the rest of the layers will start to peel off, exposing the Earth's interior. It'll start to squeeze itself from the core until it becomes similar to a pancake. Nothing can survive at this point. So much heat will be produced from the core that the planet will heat up like a microwave. All the water will disappear, and it'll look like a red dot in the solar system. And once it starts to approach the speed of light, time will freeze. The rocks and floating elements won't move and will eventually be distorted. And with enough effort, the Earth will eventually turn into a black hole. Of course, nothing like this will ever happen. According to scientists, Earth will most likely slow down in rotation. Ever since the Moon came into the picture, the Earth has been slowing down by around 4 miles per hour every 10 million years or so. That's because of the Moon's gravitational pull on our little blue planet. It'll most likely go on that way. So hey, what's your hurry?